Dear students, we have learned how two coherent sources can be obtained from a single monochromatic source of light, and then how waves emitted from the two sources of light superimpose to form interference pattern on the screen in the form of these bright, and this black means dark, bright and dark fringes. Now we would like to find the relation or some mechanism to find the position of these fringes on the screen in terms of the dimensions of the experimental setup used. For that, I assume that these two sources of light are like A and B are two sources of light which are separated from each other by a small distance, let us say d. Then I suppose that these two sources are emitting the light, and the waves emitted from these two sources, they meet at point somewhere at on the screen here at point B. I assume this way that these two waves meet at point B. Let a line, we join this line the center of the two slits or two sources on the screen in such a way that this line joins here at point C, and I assume the distance of this maxima or minima from this point is, let us say, x. I assume this distance as x. So we know that the formation of bright or dark fringe depends upon the path difference between the two waves which they travel from these two different sources of light, and this path difference between BP and AB may be seen in this diagram just by plotting a perpendicular from this point on the line here, such that we can say that N to P and A to P, both lines are equal, but the difference is only B to N. Now we are trying to find what is this B N distance, and that will be determined by using two right angle triangles. One right angle triangle we will use from B, let me just join here, to R, let us say, and other is Q here. So we have one right angle triangle PAQ, another is PBR. From these two right angle triangles, we will try to find out what is the value of hypotenuse AP and what is the value of hypotenuse BP. Then subtracting AP from BP, we will find this BN is the difference. For that, I assume the distance between B and R is capital D. Let us write down capital D. And we know this distance is small d, such that from Q to C, this will be d by 2, and from C to R, it will also be d by 2. Keeping these points in mind, we can write what is AP square. That means I want to find what is this hypotenuse. So using Pythagoras theorem, AP square will be equal to AQ square plus QP square, which gives me D square plus, now QP is equal to CP minus this D by 2, this small distance. So I will get PQ. Therefore I can write here equal to X minus D by 2 whole square. This is AP, and similarly we can write BP square is equal to BR square, this base square plus this perpendicular square, which is equal to RP square, and BR is equal to D, that is D square plus, now R to P is equal to this X from here to here plus D by 2, this portion. Therefore X plus D by 2 whole square. Now to find this distance, I have to subtract AP from BP. Therefore let us find BP square minus AP square is equal to, let us subtract this value, that is D square plus X plus D by 2 whole square minus this value, that is D square plus X minus D by 2 whole square. From this, this it will cancel out, and here we will get negative sign because this negative will make this term and this term both negative. So we get now from here X plus D by 2 whole square minus X minus D by 2 whole square. Let us open, we get X square plus D by 2 whole square plus twice X into D by 2 minus X square plus D by 2 whole square minus, or this minus plus, twice D by 2 into X. So from here X square will cancel out, D by 2 square will cancel out, and we left with these two terms, similar terms. So we get this 2 will cancel and these 2 will cancel. So we get one XD and other XD. So we get twice X and D. This is BP square minus AB square. Now left hand side can be expanded in the form of A plus B into A minus B. Therefore I will write this term as BP minus AB, BP plus AB, which is equal to 2XD. And we assume that BP and AP, this BP and this AP, both of are almost equal. If this P is not far away from C, that means P is near to C, which means we are just looking for this maxima or this maxima which is near to C. In that case, BP and CP, AP and BP will be almost equal, and therefore in that case we can write this BP and AP is equal to D. So let us write down it as BP minus AP. Only in the addition form we can write it D plus D. equal to 2xd. Further, it gives me BP minus AP is equal to 2xd over 2 capital D. That means xd over d. Now BP minus AP is nothing but it is the path difference, which is equal to, here you can say, which is B to N, that is path difference, and we can write it as path difference is equal to xd over capital D. And we know that this brightness and darkness on the screen will depend upon the path difference. And in previous case we have seen that we will get maxima or the brightness if path difference is equal to n times the wavelength, and it will be darkness if it is 2n plus 1 times half wavelength. So let us find under what condition or what is the position of the maxima on the screen. For that, for maxima, let us find for maxima path difference should be equal to n lambda, and let us equate these two. We get xd over capital D is equal to n lambda, which implies that x from center, that means x is the distance from the center of that position, that is n lambda times distance between screen and source divided by distance between the two sources. So this is the expression which gives us the position of maxima from this center, because x is this and whatever the point P is there for maxima, that will depend upon these parameters, where n is the number of maxima, which can be given by 0, 1, 2 and so on. It means by using these numbers we can say that the first maxima apart from central maxima when n is 0, first maxima will be at lambda d over small d, and you can say second maxima will be equal to 2 lambda d over small d, and the distance between these two brightness or bright points, that means this is central maxima, this is first one and this is second one. So we can find what is the distance between these two, because that if the distance is significant, only then you can find these two bright points separate, otherwise they will just mix together and you will get a general illumination. So for that, let us find the difference between these two bright points, which is called fringe width. So I want to find what is fringe width for bright points or bright fringes. That means for that it is denoted by beta is equal to x2 minus x1. That means 2 lambda d over small d minus lambda d over d, which gives you lambda d over lambda capital D, sorry. This is here we have capital D over small d. So therefore, for bright fringes, the difference comes out to be lambda d over small d. Fringe width depends on wavelength, distance between sources and screen, and distance between two slits. Let us now try to find where is the dark fringe. For dark fringe, for fringe or dark points, we have minima, that is minima positions. We have a path difference condition for minima, that is path difference must be equal to 2n plus 1 lambda by 2. And if we equate this path difference condition here, because we know that the path difference should be equal to this much, for that we can write it should be equal to, we have seen that path difference here is xd over capital D, so let us write x small d over capital D, which gives us x is equal to 2n plus 1 lambda capital D over small 2d. So for first minima, let us say x1 will be equal to, because here we will be having 1, so we will be having 3 by 2 lambda d over small d. And for second minima x2, we will put here 2, we will be having 5 by 2 lambda d over small d. And the fringe width for that, here fringe width mean I want to find distance between this darkness and this darkness. What is the total distance? That gives me a fringe width of the dark fringe. The fringe width is equal to x2 minus x1, that is 5 by 2 lambda capital D divided by small d minus 3 by 2 lambda d over small d, which gives you this is equal to 2 by 2, that is equal to 1, and we get lambda d over small d. It means the fringe width, that is beta in this case, lambda d over small d, and fringe width for bright fringes and fringe width for dark fringes is same. And it shows that this fringe width, that means the distance between two bright points and distance between two dark points, the dependence is same, and this depend upon the wavelength. Higher the wavelength, larger will be the distance, so the separate fringes can be observed. If d is large, that means distance between the sources, coherent sources and screen is large, then the fringes will be seen separately clearly. And one more dependence is small d, that is distance between two slits here, and if these two slits are so close, then denominator will be small and the beta will be large. Therefore, in that case also the fringes will be seen separate. So therefore we have to see one more point here which is very important, that is beta or separation does not depend upon the order of the maximum. Means it does not depend whether maxima is first or bright point is first or second or third. That it shows that the interference fringes have the same fringe width, whether these are first, second, or third, fourth, or next. So fringe width for all the fringes in interference pattern is same. So that's all about the interference pattern. Now we know that how can we find the interference pattern on the screen and where are the dark and bright fringes, dark points, and how they are created dependent on the wavelength and the amplitudes. Other conditions all are explained in these lectures. So thank you very much for watching these videos.